It is a known rule in software engineering. A system that performs perfectly in a pristine test environment will often fracture the moment it encounters heavy, real-world load. When developers test AI code generation in isolation, the results appear flawless. The model doesn't have to navigate external dependencies, state management, or legacy infrastructure. This diagram shows that frictionless environment. You ask the model to write an isolated script, and it returns clean output. But deploy that model into production, and the AI collides with legacy systems, security boundaries, and complex routing requirements. Enterprise architecture requires backward compatibility. It enforces strict performance trade-offs and demands precision from ambiguous business requirements. The model is no longer operating in a vacuum. Deploying AI into a live system exposes it to severe operational risk. A single incorrect assumption made by the model will propagate defects across the entire architecture. The root cause of these production failures is rarely the model itself. The failure stems from a specific architectural flaw known as the monolithic prompt. Look at the pressures applied to the model here. Developers are writing single, massive prompts that instruct the AI to act as the analyst, architect, implementer, and tester, all at the exact same time. In standard software engineering, this approach is called the explicit removal of the separation of concerns. No senior engineer would write a single 10,000-line function to simultaneously handle API routing, complex business logic, database persistence, and user authorization. Yet this is exactly how teams treat large language models. They deploy the AI as an omniscient black box, discarding decades of established modularity rules. Expecting a model to parse, generate, and validate highly entangled responsibilities in a single pass is not an AI limitation. It is bad system design. When monolithic prompts fail, developers often blame token limits, assuming the model hallucinates simply because it was fed too much information. This is a misdiagnosis. Massive context, providing dense PRDs, service contracts, and incident history, is mandatory for high reliability, provided the model is executing a single, narrow task. This graphic isolates the true point of failure, unstructured cognitive overload. The breakdown occurs when deep context collides with competing objectives, shattering the output into unstable code. This matrix maps out the specific design violations caused by that overload. We see tight coupling at the top, where requirements and implementation are entangled in one opaque step. But the immediate dangerous consequence is shown directly below it: poor observability. Because there are no intermediate boundaries to inspect, the model fills in logic gaps silently. You only see the final compiled output. Without explicit interfaces between reasoning steps, the exact moment a defect enters the logic chain is invisible. Debugging the AI's reasoning becomes impossible. This lack of observability triggers what we call the failure cascade, a process where silent defects travel undetected through generated code. This flowchart illustrates the cascade. It starts in requirements with one incorrect assumption. Because steps are tightly coupled, that bad premise infects the architecture, propagating directly into the implementation code. The most dangerous phase is here: the tests pass. The test suite returns a green checkmark because the AI generated those tests based on its own flawed initial premise. The system is perfectly internally coherent and completely externally wrong. We map this specific danger here as the fluency trap. The code compiles. The tests exist, but beneath that polished surface lie unchecked invariants and missing rollbacks. AI output is highly fluent, which makes it deceptive. A self-confirming review loop, where the same prompt generates the code and judges the result, lacks the adversarial tension required for true production safety. To build reliable pipelines, engineering teams must stop treating the LLM as a self-correcting human teammate. The model is simply a probabilistic hardware component, and like any highly volatile component, it requires strict containment. This diagram details that containment strategy. The probabilistic AI model is securely nested inside heavy, deterministic border walls of explicit constraints and validation gates. In standard software architecture, complex systems are made safe by isolating responsibilities and enforcing explicit interfaces at every boundary. That foundational engineering principle does not stop being true just because the component processing the data is an AI model. System reliability will never be generated by the probabilistic model itself. It is created by the rigid, deterministic architecture built to constrain it. This chart maps the physical transformation required to achieve that reliability. We must dismantle the tangled monolithic prompt on the left and replace it with the highly structured staged execution pipeline on the right. This 6-stage AI engineering pipeline maps a sequence from requirements down to structured review. Every step has one dominant objective and an isolated failure surface. Notice the discrete documents generated at each stage: a requirement risk report, an architecture blueprint. These are serializable artifacts. They create explicit contracts that allow another engineer, or distinct AI instance, to audit the reasoning before the next step begins. Look at the rigid validation boundary here, separating code generation from code judgment. The creation and the evaluation are completely isolated. Reliability in AI directly mirrors reliability in traditional software. It is achieved through a sequence of bounded transformations, not a single request. This is the core imperative for technical leads and architects. Do not optimize for one giant prompt. Optimize for a workflow that can be trusted.